Ladies and gentlemen, welcome to this seminar on Thermogravimetric Analysis, or TGA as it is usually called. TGA is a technique frequently used in thermal analysis. Its main use is to characterize materials by measuring their change in mass as a function of temperature. The properties and behavior that can be measured by TGA include composition, purity, decomposition reactions, decomposition temperatures, and absorbed moisture content. TGA is often used together with differential scanning calorimetry, DSC, because the two techniques provide complementary information which often facilitates the interpretation of a thermal analysis experiment. In the course of the webinar, I would first like to explain the basic principles of TGA and DSC, and then describe the Mettler-Toledo TGA DSC-1, a high-performance TGA instrument that can simultaneously perform TGA and DSC measurements on the same sample. I also want to point out a number of important design features and options. Finally, I will present several practical examples to illustrate different application possibilities that the TGA DSC-1 instrument offers. Thermogravimetric analysis measures the mass of a sample as it is heated, cooled, or held at a constant temperature in a defined atmosphere. The picture on the left shows a match that has just been ignited. The burning process produces gaseous combustion products that are released into the atmosphere. The mass of the match steadily decreases, finally leaving just ashes behind. The burning process of a match can easily be measured by TGA. A typical mass loss curve of a polymer is shown on the right. The different steps are numbered 1 to 5 next to the curve. 1 is the loss of volatile components such as moisture, solvents, and monomers. 2. Decomposition. 3. The atmosphere is switched from nitrogen to oxygen. 4. Combustion of carbon. 5. Inert inorganic residue of ash, fillers, or glass fibers. The gaseous products that are evolved can be analyzed using hyphenated techniques, for example by coupling a Fourier transform infrared spectrometer, FTIR, or a mass spectrometer, MS, to the thermal balance of the TGA instrument. The curve in the diagram shows only the mass loss. In fact, much more information can be obtained from a single measurement. I will explain how this is achieved with the aid of the next slide. We see a schematic view of the TGA DSC-1 instrument. It combines a special furnace, shown in the middle, and a highly sensitive balance on the right. In the TGA DSC-1, the scale pan is replaced by a DSC sensor. The balance cell on the right is thermostated to minimize environmental influences. The balance beam is connected to the TGA DSC sensor. The support for the sample and reference crucibles is located in the middle of the furnace. The horizontal design of the furnace helps to minimize possible turbulence due to thermal buoyancy and the purge gas flow. The furnace temperature is controlled by the temperature sensor located below the furnace. The furnace is shielded on both sides by baffles, and the entire volume is purged with a constant flow of gas. In addition, the sample can be purged with a reactive gas that flows through a capillary located near the sample crucible. The volatile and gaseous combustion products from the sample, as well as the purge gas and reactive gas, leave the furnace through the gas outlet on the left. Analytical instruments can be connected to this outlet for evolved gas analysis. I now want to look at the TGA DSC sensors in more detail. One of these sensors is shown in the bottom left corner of the slide. The schematic diagram above displays a sensor with sample and reference crucibles. The temperature difference between the sample and the reference is measured by means of thermocouples located directly below the crucible support. The signal is calibrated and adjusted to produce a heat flow signal. The resulting signal is analyzed in the same way as for DSC. The schematic curve in the lower right corner of the slide shows a typical melting peak. The curve provides valuable information such as the enthalpy of melting, the melting point, and the specific heat capacity. As in a dedicated DSC instrument, the heat flow is calibrated and adjusted at different temperatures using certified reference materials. The TGA DSC1 generates three different curves, namely the weight loss curve, the derivative of the weight loss, or DTG curve, and the heat flow curve. The example shows the three curves obtained from the analysis of a sample of polyethylene terephthalate. The TGA DSC1 can be equipped with three different sensors. The TGA DSC sensor has 6 thermocouples located directly below a protective ceramic support, which measure the sample and reference temperatures. The TGA DTA sensor has 2 thermocouples that measure the sample and the reference temperatures. The support is made of platinum. The differential measurement improves the signal-to-noise performance of the sensor compared to that of a sensor with only 1 thermocouple. The TGA SDTA sensor consists of a platinum support with a thermocouple that measures the sample temperature. A modeled reference temperature is used for the DSC signal. All 3 sensors generate a DSC signal which provides additional information that is otherwise not revealed by TGA alone. For example, solid-solid phase transitions. The DSC signal is generally less sensitive than the signal from a dedicated DSC instrument. The TGA DSC1 uses a top-of-the-line Mettler-Toledo ultra-micro balance to measure sample weight. The balance is unique in every respect. It provides ultra-microgram resolution over the whole weighing range and measures up to 50 million resolution points continuously. This means that changes in mass of a 5 milligram sample are determined to 0.1 microgram. The balance uses automatic internal adjustment. External adjustment with certificated weights is also possible. And finally, samples can be weighed in semi or fully automatically, or using an external balance. The type of crucible and the material used are very important for achieving optimum results. Mettler-Toledo offers different types of crucibles for different sorts of samples and experiments. Some of the most commonly used crucibles are displayed in the slide. The standard TGA alumina crucibles are available in different sizes. These are the most frequently used crucibles and can be reused after cleaning. Platinum crucibles are used to achieve a high-quality DSC signal. Aluminum crucibles are cheap and can be used for temperatures up to about 600 degrees Celsius. Sapphire crucibles are used to measure liquid metals at high temperatures. Other crucibles may also be used, depending on the sample and measurement requirements. Crucibles are normally used without a lid. For applications that require a self-generated atmosphere, the crucible should be closed by a lid with a small hole. Special aluminum lids are available to prevent contamination and evaporation before the measurement. The TGA DSC-1 can be fitted with optional accessories for specific applications. The upper part of the slide shows 3 different versions of the TGA DSC-1. The standard version includes the Smart Sense terminal, shown on the top right-hand side of all 3 instruments. The picture in the middle shows an instrument fitted with a sample robot. The robot can process up to 34 samples, even if every sample requires a different method and a different crucible. In the picture on the right, we see a TGA DSC-1 equipped with a gas box. This can automatically switch, monitor, and control gas flows, and switch from an inert gas to a reactive gas atmosphere during a measurement. The lower part of the slide shows different interfaces used for hyphenated techniques, namely mass spectrometry, MS, Fourier transform infrared spectroscopy, FTIR, and sorption. All TGA DSC-1 instruments can be connected online to a mass spectrometer or a Fourier transform infrared spectrometer to analyze gaseous decomposition products. This technique is known as evolved gas analysis and yields additional information about the sample and so enables you to interpret measurement curves with greater certainty. A humidity generator can be attached to the TGA DSC-1 equipped with a large furnace in just a few minutes. This option allows materials to be analyzed under precisely defined conditions of relative humidity and temperature. The next slide shows some of the different measurement possibilities that the TGA DSC technique offers. TGA DSC measurements can be performed dynamically using a linear temperature ramp or isothermally. Temperature ramps are used to investigate temperature-dependent processes such as the loss of moisture, composition, and chemical reactions. Isothermal measurements are mainly used to determine the oxidation-induction time of materials or to study the release or absorption of moisture. The atmosphere is often switched from inert to oxidative to burn the carbon black and determine the ash or filler content. Measurements under reduced pressure or vacuum are employed to separate overlapping effects of vaporization and decomposition. The simultaneously measured DSC heat flow signal records exothermic and endothermic events such as the glass transition, melting, crystallization, chemical reaction, and phase transitions. In the following slides, I want to show examples of each of these 4 measurement possibilities. Let me begin with the temperature ramp. In this example, 11 milligrams of calcium oxalate monohydrate was heated at 30 Kelvin per minute in a nitrogen atmosphere. The weight loss curve shows 3 well-separated steps that correspond to the stoichiometric decomposition reactions of the substance. The first step is due to the loss of water of crystallization. The second step is due to decomposition with the formation of calcium carbonate and release of carbon monoxide. The final step is also caused by a decomposition reaction involving the formation of calcium oxide and the liberation of carbon dioxide. Here we see an example of an isothermal measurement. Zeolites that have been preconditioned with a defined amount of moisture are used to check and adjust the balances in infrared drying instruments. The amount of moisture can be determined in an isothermal measurement using the TGA DSC-1. The measurement was performed at 100 degrees Celsius in a 30 microliter alumina crucible. After 400 minutes, the weight is stable. The mass loss is approximately 8%. The next example illustrates the use of gas switching at 600 degrees Celsius. The upper diagram shows a sample of rubber that was first heated to 600 degrees under inert conditions. In this temperature range, volatile liquid components such as plasticizers vaporize. This is followed by pyrolysis of the polymer shortly afterward at about 400 degrees. At 600 degrees, the atmosphere was switched from nitrogen to oxygen, which results in combustion of the carbon black additive. Inorganic components remain behind as a residue at 800 degrees. Evaluation of the TGA curve gave the following sample composition: 6.4% plasticizer, 68.2% polymer, and 21.8% carbon black, and a residue, mainly zinc oxide, of 3.6%. The lower curve in the diagram is the DTG curve. In this case, the curve was used to set the limits for the overlapping effects of vaporization and decomposition. Now let me describe an experiment that illustrates the importance of measurements under vacuum or reduced pressure. Oils are often used as plasticizers and elastomers. Usually, decomposition of the elastomer begins before the oil has completely vaporized. The two effects overlap in this temperature range. This makes it difficult to quantify the oil content. In such cases, it is advantageous to measure the elastomer samples under vacuum in order to separate the two effects. In this example, the dotted lines display the weight loss curves of SBR samples with and without oil at ambient pressure. The continuous lines show the corresponding curves measured under vacuum at a pressure of 1.2 kilopascals. We notice that vacuum hardly influences the measurement curve of SBR without oil. In contrast, when SBR with oil is measured under vacuum, the vaporization of the oil and decomposition of the elastomer are almost completely separated. Here again, the steps are more clearly separated in the DTG curve. At ambient pressure, the two peaks overlap, whereas under vacuum, the peaks are well separated. The four examples just presented illustrate the wide application range of the TGA DSC technique. This slide summarizes the main areas of application. One important application is compositional analysis. For example, the content of volatiles, polymers, carbon black, or fillers and polymers. In the polymer field, it is important to know the temperature range in which the polymer is stable and the range in which decomposition occurs. The TGA DSC technique provides information about the purity of the sample if the stoichiometry of the reaction is known. The results of isothermal or temperature-ramped measurements can be used to determine reaction kinetics. Other applications include the investigation of desorption or adsorption processes, evaporation behavior, and the influence of reactive gases. Evolved gas analysis of decomposition products using hyphenated techniques such as mass spectrometry or Fourier transform infrared spectroscopy provides additional information about the sample. TGA DSC has many potential applications and is used in a wide range of industries. The slide presents an overview of the different industries and applications. Thermogravimetric analysis provides quantitative information on the composition and thermal stability of many types of materials. The method is fast and can be used with very small amounts of sample. The DSC signal can also be quantitatively evaluated, allowing glass transition and melting temperatures to be determined. The TGA DSC-1 is an exceptionally versatile instrument for the characterization of physical and chemical material properties under precisely controlled atmospheric conditions. It provides valuable information for research, quality control, and development. I would now like to present several different application examples that demonstrate the analytical power and versatility of the TGA DSC technique. Polymeric materials often contain small amounts of carbon black for coloration and stabilization. The carbon black content can be determined by switching to a reactive gas after pyrolysis of the polymer. The example shows the analysis of a polyethylene sample. The atmosphere was switched from nitrogen to air at 600 degrees Celsius. Evaluation of the pyrolysis weight loss step yields a polymer content of 97.7%. The carbon black content is 2.1%. The DSC curve shows the endothermic melting peak of polyethylene at about 130 degrees. Pyrolysis of the polyethylene produces an endothermic peak. This is followed by the strongly exothermic combustion of carbon black immediately after switching to oxygen. Kaolin is a white mineral used in the paper industry as a filler in plastics and for the manufacture of porcelain. The example shows the measurement of 3 samples of kaolin containing different contents of kaolinite. Chemically, kaolinite is a hydroxide of aluminum silicate and is the main constituent of kaolin. Kaolinite dehydroxylates between 450 and 600 degrees Celsius and is responsible for the weight loss steps in the TGA curves. The DSC curve of kaolin A shows a small peak at about 575 degrees. This peak is characteristic for the solid-solid transition of alpha to beta quartz. The exothermic peak at about 1000 degrees is due to the formation of mullite. In a hermetically sealed crucible, glucose monohydrate melts in its water of crystallization without weight loss. The first peak in the DSC curve resembles the melting of a eutectic mixture of glucose and water. The excess glucose then melts up until about 130 degrees Celsius. In an open crucible, the substance behaves very differently. The water of crystallization vaporizes between 50 and 140 degrees, resulting in a broad endothermic peak in the DSC curve. The anhydrous glucose then begins to melt at about 145 degrees. The mass loss of 9.1% corresponds to the stoichiometrically expected value. This slide shows an example of the use of the MaxRes software option. When MaxRes is activated, the heating rate varies automatically depending on the rate of change of weight. This allows overlapping weight loss steps to be optimally separated in the shortest possible time. The example shows the dehydration of copper sulphate pentahydrate. At a constant heating rate of 25 Kelvin per minute, the first two weight loss steps are not properly separated. Using MaxRes, the separation is better in a shorter measurement time than at the relatively low heating rate of 5 Kelvin per minute. MaxRes saves time and is a good tool for method development. In this application example, the full temperature range up to 1600 degrees Celsius was used. In the TGA curve, we see that gypsum, calcium sulfite dihydrate, loses its water of crystallization below 300 degrees Celsius to form calcium sulfate. The calcium carbonate present as an impurity decomposes at about 700 degrees Celsius. Decomposition of the calcium sulfate occurs in several steps from about 1200 degrees Celsius onward. The simultaneously recorded DSC curve shows two additional effects due to solid-solid transitions. These are the transitions from gamma to beta calcium sulfate at about 390 degrees and from beta to alpha calcium sulfate at 1236 degrees. The latter compound melts slightly below 1400 degrees Celsius and is observed as a sharp endothermic peak. This slide shows an example from the pharmaceutical industry that uses mass spectrometry. Many active pharmaceutical substances are recrystallized from solvents. As a result, residues of solvents often remain in the product. A hyphenated technique, such as a TGA-MS combination, is ideal for detecting and identifying such undesired residues. In this example, the active substance was recrystallized from methanol and acetone. The presence of these two solvents is confirmed by the peaks in the M/Z43 and M/Z31 MS fragment ion curves. The results indicate that the weight loss step at 200 degrees Celsius is almost entirely due to the elimination of acetone. The upper and lower diagrams illustrate the two main methods used to calibrate and adjust the TGA DSC-1. The upper diagram illustrates temperature and heat flow adjustment. This is normally performed using certified pure metals such as indium, zinc, and aluminum. Gold and palladium can be used to calibrate and adjust the temperature and heat flow up to the maximum temperatures specified for the TGA DSC-1 furnaces, 1100 degrees Celsius and 1600 degrees Celsius. The lower diagram shows the use of the Curie transition temperatures of certain ferromagnetic metal or alloy reference materials to calibrate the TGA temperature scale. The reference material is measured in a magnetic field and shows an apparent loss of weight at the Curie temperature. Thermogravimetric analysis is an excellent technique for characterizing the thermal properties of materials such as plastics, elastomers and thermosets, mineral compounds and ceramics, as well as for chemical and pharmaceutical products. The slide summarizes the features and benefits of the TGA DSC-1. The Mettler-Toledo TGA DSC instrument simultaneously measures weight loss and heat flow. For high-throughput applications, a sample robot allows easy automation of entire sample series. Even different types of crucibles can be measured with individual temperature programs. The modular concept of the TGA DSC permits options such as the sample robot, gas box, or hyphenated techniques to be added later on if required. Flexible calibration procedures allow the instrument to be calibrated and adjusted over the entire temperature range from room temperature to 1600 degrees Celsius. The TGA DSC is the ideal instrument for manual or automated operation and production, quality assurance, or research and development. Finally, I would like to draw your attention to information about thermogravimetric analysis that you can download from the Internet. Mettler-Toledo publishes articles on thermal analysis and applications from different fields twice a year in UserCom, the well-known Mettler-Toledo biannual technical customer magazine. Back issues can be downloaded as PDFs from www.mt.com/usercoms. The slide lists a number of UserCom articles on thermogravimetric analysis. In addition, you can download information about webinars, application handbooks, or information of a more general nature from the Internet addresses given at the bottom of the slide. Information about application handbooks, webinars, training, or thermal analysis in general can be obtained from the Internet addresses shown on this slide. This concludes my presentation on thermogravimetric analysis. Thank you for your interest and attention.